Okay. Today is the last class of this semester. In today's class, I briefly introduce Krylov subspace methods. In numerical linear algebra, there are two broad classes of algorithms for the solution of linear systems. The first class, recall the direct method. Direct method usually a direct method usually mean a Gaussian elimination or its variance. Gaussian elimination and its variance are usually used to solve large and dense linear systems. But when linear systems is sparse, we usually don't use Gaussian elimination because Gaussian elimination requires large storage. The second class is the class of iterative methods, just like those methods that we saw in section 9.4. An iterative method, the advantage is storage is cheap. But disadvantage is it just get closer and closer to the exact solution of a linear system. Usually, it doesn't reach the exact solution. It cannot exactly get the exact solution usually for an iterative method. But a Gaussian elimination can exactly obtain exact solution of the linear system, right? After you finish the elimination, then you can get the exact solution. Now today, Krylov subspace method lie between direct method and iterative methods. A Krylov subspace method itself is an iterative method and also can exactly obtain solution of the linear system in a finite number of iterations. So we usually call Krylov subspace methods semi-direct methods. It can attain exact solution of a linear system, and also it is a iterative method, lie between direct method and iterative method. Okay. Now let me erase and then move the second half of this page. Okay. Suppose we want to solve a linear system. Here, I assume the linear system sparse. If the linear system coefficient matrix is non-sparse, it is dense. We apply Gaussian elimination or one of its variance. Here, A is sparse. Theoretically, it can be proved arbitrarily pick a guess to the solution of the linear system. X0 arbitrary pick. It can be so that the exact solution, X star of the linear system, is always in this affine subspace. Here, N is the dimension of the matrix A. The dimension of matrix A. Yeah, X0 arbitrary pick. Exact solution of the linear system is always in this subspace. How to prove it? The proof is not difficult. Okay. Arbitrary pick X0. Then compute its residual vector. Yeah. Right hand side minus A times X0. This vector is called the residual vector of X0. Then for matrix A and this vector R0, we can find a polynomial P. The degree log greater than n. N is the size of the matrix, and P also the constant term is 1. Okay, we can find P. Constant term is 1, and then C1 T plus C2 T squared plus Cn Tn. For any matrix, actually, any matrix A, any vector R, there is a polynomial whose degree log greater than n and whose constant term is 1, such that P times A times the vector R is a 0 vector. Theoretically, we can find such a polynomial. Say, for example, the characteristic polynomial of the matrix A. Okay, characteristic polynomial. Polynomial. Then plugin A in T. This is a matrix. This matrix must be 0 matrix. This is well-known result. Yeah, characteristic polynomial is one example. Okay, now from this equation, I plug in A in T, multiply P of A by R0, then we get this equation. A R0 and so on. Cn An R0. Then this is a 0, right? This is 0. Okay, now what is R? R is a B minus A times X0, and then plus C1 A R0 and so on. Cn An R0. It is equals to 0. Okay, now keep the vector B on the left side. Move all other terms. Let me see. Move all the other terms to the right side. Then we get B is equal to A X0 minus C1 A R. Yeah, minus Cn An R0. Now on the right side, factor out 1A. Then X0 minus C1. This A, I take this A out, R0, and then so on. The last term, take 1 A out, so A M minus 1, R0, right? R0, yeah. So therefore, this vector, this is a vector, okay? This vector, A times this vector is equal to B. So this vector is exact solution. Exact solution. So therefore, exact solution x star is x0, right? X0. Then this part is a vector in this space. In this space, a space plus a vector is called an affine space. Yeah, x0 plus this space, we call it an affine space, not exactly space, but an affine space. So therefore, exact solution is in this affine space for any x0. This can be proved by using one well-known result in linear algebra. Okay. Okay. Now, let me erase this part. I have proved this relation. Okay, relation. So I erase. Okay. Then a Krylov subspace method. It is a iterative method. In the cave iteration, a Krylov subspace method search for some approximation, say xk. Xk is an approximation to the exact solution of the linear system. Search, find some approximation from this affine subspace. Here, k. Okay, when k is n, exact solution is in this affine subspace. Now k less than or equal to n. Okay. So in the cave iteration of a Krylov subspace method, the method look for some approximation from this affine subspace where k less than or equal to n. Okay. Because of this property, when k is equal to n, that means in other words, in the nth iteration, exact solution is in this affine subspace. So in nth iteration, a Krylov subspace method is guaranteed to obtain the exact solution of the linear system. So Krylov subspace method doesn't like the iterative methods introduced in section 9.4. In section 9.4, those iterative methods converge to the exact solution, but probably never reach the exact solution. But Krylov subspace method different. Okay, guarantee a maximum of n iterations. A Krylov subspace method is guaranteed to obtain exact solution of this of the linear system. Linear system. Okay. There is a term. Okay. Here. For any vector, a space of this form is called a Krylov subspace. So that's why we call, because a Krylov subspace method look for solution in affine Krylov subspace. So we name those methods Krylov subspace methods. In history, okay, the first Krylov subspace method is yeah, let me erase. Okay. Okay. In history, the first Krylov subspace method is the conjugate gradient method, briefly CG. Okay. Developed by these two mathematicians in 1952, and also Man-Chung also obtained a similar version of CG method. So actually, these three people, okay, they independently develop CG method. Yeah, CG method is was selected as one of the top 10 algorithms in numerical linear algebra in the last century. Okay, yeah, this is very famous. Okay, yeah. The CG method solve linear system, but there are some requirements on the coefficient matrix. Yeah, CG solve linear system. Of course, A is sparse and large, but it requires A is symmetric. Okay, and positive definite. What it means? The eigenvalues of this matrix A are positive or are positive. We assume A symmetric and eigenvalues all are positive. Then we can apply CG to solve the linear system. Yeah. Here is the CG algorithm. The algorithm is log long. Okay, log long. Just how many lines? Just 1, 2, 3, 4, 5 lines. Yeah. A vector transpose times the vector. This is an inner product. So in CG method, two main operations. One is inner product. Main operation. Okay, yeah, inner product. Here, inner product. Here, inner product and inner product. The second main operation in CG is a matrix times a vector. Yeah, a matrix. A vector multiplication. Yeah, multiplication. Two main operations. Okay, per iteration. Yeah, per iteration in CG. We need to perform a matrix times a vector. Yeah, A times PK. Compute it, then keep the result for the use here and also here. So we don't need to compute A times PK 3 times. Compute it, keep the result, then use the result here and result here. So per K iteration, only one matrix vector multiplication. Actually, this algorithm very popular. Okay, in engineering. Okay, in engineering, usually linear systems arising from numerical PDE. Okay, they are usually symmetric and positive, definite. Surely use CG to solve linear system. Okay. Let me erase. About the storage of CG. To run this algorithm, of course, we need to store matrix A. Matrix A here is sparse. Most of the entries are zeros. We don't need to store zeros. We only need to store non-zero entries. So the storage of A is cheap. Okay. And also we need to keep this vector, right? So we should have a space store X. And also we should have a space to store R. So R. And also we need to keep PK. So the storage requirement about CG is store the matrix A and free vectors, and also maybe one more. After you compute A times PK, keep this vector. So a matrix and free vectors. That's it. Yeah. So it doesn't like Gaussian elimination. Gaussian elimination, your computer, okay, to run Gaussian elimination, your computer should be able to store n square so many entries. Yeah. A, most of the zeros are, most of the entries are zeros. Non-zero number, the number of non-zero entries usually is some constant, small constant, times n, the size of A. Yeah. A vector, how many entries? N entries. So in total, about C plus 1, 2, 3, n plus this n. So 4n. 4 times n. Yeah. So the storage about CG roughly is so much, but Gaussian elimination storage is n square. When n is large, n square, of course, much larger than this number. Right? Yeah. About CG, here are some properties. The first property is the residual vector allocate. What allocate is? Allocate is a B right hand side minus A times xk. Xk, the estimate of the exact solution in k iteration. Okay, so residual vector allocate is theoretically, okay, suppose a low round of error, then allocate is orthogonal or the previous residue vectors. Second property. The second property is the estimate of the exact solution in k iteration minus the exact solution. The distance in terms of this long, okay, this is a vector long. This is a vector long. It can be proved, okay. Vector v, vector V transpose times A, the coefficient matrix, times B, then take square root. This is along. The distance between the estimate in the cave iteration and the exact solution in terms of this long is bounded by this number. Bounded by this number. Yeah. Kappa is the largest eigenvalue of the matrix A over the smallest eigenvalue. Yeah. So if kappa is large, then this quotient, this ratio is close to 1. In the case, CG method is converges slowly, right? Because this number close to 1, okay, doesn't decrease. Okay, this number to A, this vector doesn't decrease faster. Okay, in the case. Okay, but when this ratio is less than 1, much less than 1, then this vector will decrease very fast. As a result, CG converge very fast. So we consider this number as the condition number of the coefficient matrix A. When this ratio close to 1, we say that when this number is large, not close to 1, yeah, this number is always less than or equal to 1. When this number is large, then this ratio close to 1. When this number is large, we say that matrix A is U condition. U condition. When this number not large, then this ratio is much less than 1. In the case, we say that matrix A is well conditioned. Well conditioned. Okay. So this is actually is a condition number. Condition number. The largest eigenvalue over the smallest eigenvalue. We use it as condition number of the matrix A. Condition number is large. A Krylov subspace method converges slowly. Okay, slowly. And also there is one more nice property about CG. If matrix A has exactly P distinct eigenvalues, say submatrix, say A, say 5 by 5. This A has 5 eigenvalues, but 5 eigenvalues, only 2 are distinct. Say for example, 1, 1, 1, 2, 2, 5 eigenvalues, but only 2 eigenvalues are distinct. Then in the case, when you apply CG to solve the linear system, 2 iterations guaranteed to get the solution of the linear system. Yeah, here. If A has P distinct eigenvalues, then CG will converge in exactly P iterations. Because of this property, to solve a linear system, we don't directly apply CG to this linear system. Rather, we first find some matrix M. The matrix M close to matrix A. And matrix M is inverse, is easy to obtain. Okay? Then first find M and then apply M inverse to the linear system. Yeah. Because M is close to the matrix A, this new coefficient matrix, their eigenvalues are cluster around the number 1. Yeah, around 1. Okay, because when M is exactly A, for example, in this extreme case, this is A inverse times A. Its eigenvalue exactly 1. Exactly 1. But now M close to A, so M inverse times A. Eigenvalues cluster around 1. Right. Then apply CG to solve this new linear system and converge very fast, very fast. Yeah, this matrix M, we give a name to it, preconditional. Okay, yeah. To solve a linear system, usually we don't directly apply CG to solve it. Instead, first look for M. M close to A. M inverse easy to get. And then apply CG to this new linear system to make the convergence fast. Okay, matrix M is called a preconditional. CG, of course, is not perfect. Why it is not perfect? CG requires A coefficient matrix to be SPD, symmetric and positive, definite. CG cannot solve a general linear system. But anyway, it is the first Krylov subspace method. Okay. All right, now next page. The second Krylov subspace method in history is a CG conjugate gradient, the second Krylov subspace method by conjugate gradient method. Yeah. 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 By conjugate gradient method, briefly by CG. This method was proposed in 1976 by Fletcher. Okay, by Fletcher. By CG, now this time can solve a general linear system. Actually, not only solve a general linear system, actually this algorithm solve 2 general linear systems simultaneously. Okay, yeah. Solve which 2? Yeah. Yeah. This 2. A transpose X, let me give X hat, and then B hat. Yeah. This algorithm solve 2 general linear systems simultaneously. Yeah. Arbitrarily take initial guess X0 to this linear system and X hat to this linear system. Okay. And then run this follow. Again, the main operations, 2 main operations. See, inner product, right? And then matrix vector multiplication. Yeah. See, yeah. This is you need to compute A transpose times a vector. Times a vector. Yeah. 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 And also A times a vector. A times a vector. Times a vector. Yeah. So inner product and matrix multiplication. That's it. Okay. That's it. Okay. Yeah. 2 main operations. Okay, now let me erase and then move down. Again, storage is cheap. Okay, to run the algorithm, store matrix A, suppose a sparse, and then store this, okay, A transpose. And also, you need to keep X hat, R hat, P, and P hat. So, two sparse matrices and 6 vectors, then you can run this algorithm. Some properties, okay. Number one, BiCG solve two linear systems simultaneously. And also, the residue vector associated with this linear system is orthogonal. The residue vectors associated with this linear system. And also here, residue vector associated with this linear system is orthogonal to the residue vector associated with this linear system. Yeah, we call this bi-orthogonal. Okay, bi-orthogonal. Similarly to CG, if A has P distinct eigenvalues, BiCG will converge to the exact solution of the linear system in exactly P iterations. Then BiCG is perfect, not perfect, okay? Not perfect, actually. Low algorithm is perfect, okay? Low algorithm is perfect. What is the drawback of BiCG? BiCG requires A transpose to run the algorithm. Why A transpose is a drawback? In some applications, it is possible we only know matrix A, but don't know A transpose. But of course, you can from A to get A transpose, but time consuming because when A is large, you need to write algorithms, write codes, C code, C++, code, write codes to store the entries of A efficiently, so that when the computer assess the entries of A, the time to assess the entries of A should be as small as possible, should be minimized. Write such a code to store matrix A. Not an easy job, okay? Not an easy job. So when A is large, people usually don't want to write code to store A transpose. A second situation is, in some applications, we don't know A transpose. In BiCG, the main operation is A times a vector, A transpose times a vector. We don't need to know A, actually. We just need a black box. What the black box is about? Enter a vector V into the black box. Then the black box output you A times V. That's it. We just need a matrix times a vector to run the algorithm. So in some extreme cases, even the matrix A, we don't know. Let alone A transpose. This is a drawback, okay? A drawback. Yeah, in some applications, only A available, not A transpose. Or in some extreme case, even A not available. Yeah. So to overcome this drawback, let me erase. Okay. All right. Yeah. Next page. In 1984, Sunnyville overcame the problem. Okay, CG. The problem with by CG is it requires A transpose to run the algorithm. Now, this mathematician developed a new method. In this new method, it doesn't need A transpose, and also the name of this method is a gradient square method, briefly CGS. CGS solve general linear system. Okay, yeah, matrix A, general matrix, but it doesn't require A transpose times B to run the algorithm. This is an advantage in some computation. You see, yeah, here, compute A times P. After get A times P, then take transpose. Okay. Here, A times P. But after we compute A times P, keep it now for this step. But here, a second A times a vector. So this algorithm, two matrices times a vector. Yeah, two matrices times a vector to run this algorithm. And also this is inner product. Yeah, inner product. Yeah. Yeah, this is an advantage of CGS. And the storage requirement of CGS is not big. Okay, it's not big. Yeah. To run this algorithm, you need to store A, no A transpose, and also need to store these 6 vectors. These 6 vectors. Yeah. Yeah, some properties. A nice property, it doesn't require A transpose. A second property is, of course, when A has P distinct eigenvalues, CGS theoretically, okay, converge in P iterations. But CGS is perfect, not perfect. What is wrong? What is the problem with CGS? The computed residue fluctuates. That means that ROK residue, the two law, yeah, the two law, okay. It doesn't decrease smoothly, but some iteration large, some iteration small, then large, small, large, small. This is not. This is a drawback. Okay, this drawback. Yeah. The computed residue fluctuates, not decrease smoothly. Okay. Okay. Now to overcome this drawback, in what year someone developed a new method? Yeah, CGS was developed in 1984. In 1992, Vander Wast, this mathematician, improve the drawback of CGS by introduce some smoothing mechanism into CGS, so that to make residue, the lawn goes down smoothly. Yeah, smoothly. Yeah. So this is he named his method by conjugate gradient stabilized method, briefly by CG step. Yeah, by CG. Yeah, this is by CG step. It doesn't need A transpose and also solve general linear system. Yeah. Let me see. Yeah. Okay. Yeah. These two properties are actually common property to all the Krylov subspace method. Okay. This is not common. Okay. By CG step doesn't need A transpose, but this property is common to all Krylov subspace method. Okay. Yeah. This is a brief introduction to Krylov subspace methods. So actually, how many? If you ask me how many Krylov subspace methods so far, I think more than 50 Krylov subspace methods. But I picked some representatives to present. Okay, yeah. Actually, these four Krylov subspace methods here, they are popular. Yeah, especially CG, CG and by CG step. If you are engineering, from engineering, then you should know. Okay, people are using CG and by CG step. Okay, to solve linear systems. Okay.